If I told you the only thing standing between your $1,000 smartphone and a spiderweb of cracks is a sheet of glass thinner than a credit card, you'd probably ask one question: why doesn't it shatter every time it slips out of your hand? Today, we're going inside the secretive world of Corning's Gorilla Glass factory to see how sand turns into one of the toughest, most important materials in modern life, and how a single phone call from Steve Jobs helped change the future of every screen you touch. To understand why your phone screen is so special, we have to start with that phone call. It's 2006. The iPhone doesn't exist yet. Most phones are still covered in plastic screens that scratch if you even look at them the wrong way. Steve Jobs is obsessed with changing that. He wants a glass screen that's perfectly smooth, crystal clear, and somehow doesn't scratch to death in your pocket with your keys and coins. So he calls Wendell Weeks, the CEO of Corning, a 150-plus-year-old glass company, famous for inventing the bulb glass used in Edison's first light bulbs and heat-proof glassware. Jobs basically says, "I need a new kind of glass 6 months from now at massive scale for a product I'm about to launch." Weeks tells him, "We actually invented a super tough aluminosilicate glass decades ago, but we never commercialized it. We don't have a single factory set up to make it today." Most people would have taken that as the end of the conversation. Steve Jobs doesn't. He tells Weeks, "Don't be afraid, you can do this," and then orders as much of that glass as Corning can possibly make in time for the iPhone launch. That single high-pressure conversation is what pulls an old experimental glass formula out of the lab and into Corning's factories, including a plant in Harrodsburg, Kentucky, that's about to get completely transformed. Harrodsburg sits in the middle of bluegrass and bourbon country, and from the outside, the factory looks like any other industrial site. Steel buildings, steam, trucks. Inside, it's a different world. This is Corning's oldest glass plant, built in the 1950s. It used to make things like eyeglass lenses, then later, glass for LCD screens. But once Apple calls, the entire facility transitions into something else, a 24/7 Gorilla Glass machine. Human hands basically never touch the glass. It's so pristine that only air, robots, and carefully controlled machinery ever go near it. If you've ever held an iPhone or a flagship phone from other big brands, there's a good chance the cover glass started its life on a production line here or in a sister plant like it. So how do you actually make a sheet of glass that's thin, crystal clear, and strong enough to survive drops, pockets, and thousands of swipes? The magic starts with raw materials. At its core, Gorilla Glass is a type of aluminosilicate glass. Silica sand, aluminum oxide, and other carefully chosen ingredients mixed with small amounts of proprietary elements that give it its special properties. Those raw materials are blended into a batch and fed into a massive furnace. Inside that furnace, temperatures climb above 1,800 degrees Fahrenheit, hot enough to liquefy the mix into a glowing, honey-like molten glass. Here's the first big trick: the fusion draw process. Instead of pouring molten glass onto rollers or floating it on molten tin like typical window or display glass, Corning does something clever to keep the surfaces unbelievably smooth. The molten glass flows into a huge wedge-shaped trough called an isopipe. Think of it like a wide stone weir with a sharp edge underneath. The liquid glass fills this trough, then gently overflows both sides at the same time, cascading down in two even sheets like a glowing waterfall. As those two glowing sheets of glass flow downward under gravity, they curve inward and reunite at the bottom, fusing back together into a single continuous ribbon of glass. That reunited ribbon is the sheet that will eventually become Gorilla Glass. The genius of the process is that both exposed surfaces of that sheet were once pristine, untouched liquid surfaces that only ever met air. Not rollers, not molds, not metal. The interior where the two sides fused is protected, and the outer surfaces never touched anything solid. That's how Corning gets incredibly smooth, flaw-free surfaces straight out of the furnace. Below the isopipe, this continuous ribbon of glass, maybe wider than a car, slowly descends and cools as it moves into an annealing area. Here, the temperature is carefully ramped down to relieve internal stresses so the glass doesn't crack or warp. The sheet is still moving, still vertical, like a slow-motion waterfall turning into a solid wall of glass. Precision is critical. Tiny changes in temperature, flow rate, or viscosity can warp the sheet or create ripple patterns. But when it's dialed in, you get long, perfectly uniform strips of glass with consistent thickness across the width, ready to be cut. Somewhere downstream, automated machines score and snap the cooled glass ribbon into huge mother sheets. Imagine sheets big enough to yield thousands of phone screens each. Robots stack these sheets, move them into racks, and prepare them for the next step. Up to this point, what you have is extremely smooth, high-quality glass. But it's not yet Gorilla Tough. If you dropped your phone with just this raw glass on it, it would still shatter relatively easily. The secret sauce comes next: chemical strengthening through ion exchange. Here's where Gorilla Glass gets its superpower. The glass sheets are lowered into a massive bath of molten potassium salt, usually potassium nitrate, heated to around 400 degrees Celsius. To your eyes, it would look like a pool of glowing, transparent liquid. But the real action is happening at the atomic scale, at the surface of the glass. It's like trying to fill a row of seats designed for kids with adults instead. There's not quite enough room. The bigger potassium ions push against one another and against the surrounding glass network. When the glass cools back down to room temperature, those tightly packed potassium ions are essentially locked in place, squeezed together. That creates a layer of compressive stress at the surface of the glass. Why does that matter for your phone? Cracks in glass usually start at the surface. When you drop your phone, microscopic flaws on the surface feel that impact and try to open up into cracks. But if the outer layer of the glass is already in a state of compression, squeezed inward, those tiny cracks have a much harder time spreading. It's like trying to open a zipper that's being pinched shut from both sides. That compressed skin acts like armor for the weaker interior, making the glass much more resistant to scratching, chipping, and cracking under everyday abuse. Corning designs Gorilla Glass so that this compressive layer goes relatively deep below the surface, not just a nanometer or two. The deeper and stronger the compressive layer, the more energy the glass can absorb before it fails. The result is a piece of glass that, in lab tests, can be up to several times stronger than ordinary soda lime glass of the same thickness. That's where claims like up to 5 times stronger come from. In controlled impact and bend test, Gorilla Glass can survive forces that would shatter standard glass. Once the ion exchange process is complete, the sheets are lifted out of the molten salt bath, carefully cleaned and inspected. They now look exactly like plain glass. You can't see the compressive stress. There's no superhero glow. That's one of the strangest things about Gorilla Glass. Its power is invisible. To prove it works, engineers run all kinds of tests. They drop steel balls from set heights to see when the glass breaks. They scratch it with various hardness probes. They bend narrow strips until they snap, measuring how much stress they can take. All of this happens behind the scenes long before your phone's screen ever gets cut. Meanwhile, back at Harrodsburg and similar plants, this entire process runs around the clock. Furnaces stay on 24/7 because it's incredibly expensive and time-consuming to cool them down and heat them back up. Robots and precision handling systems make sure that the glass is moved without introducing scratches or contamination. The air itself in many parts of the line is filtered and controlled to reduce particles that could cause defects. Human operators stand at control panels, watching screens full of graphs and numbers, tweaking temperatures, flow rates, and chemical bath conditions to keep everything in the sweet spot. Once the big strengthened sheets are ready, they get shipped to another set of operations, either within Corning or at partner facilities. There, the mother sheets are cut down into individual phone-sized blanks. Computer-controlled machines use diamond tools or lasers to cut the glass, drill tiny holes if needed for sensors and cameras, and shape the curved edges you feel when you swipe from the side of your phone. Those raw cut pieces then go through polishing and finishing steps to make the surface optically perfect, and fingerprint-resistant coatings can be applied. What's wild is how many devices this process touches. Gorilla Glass started with the iPhone, but it didn't stay there. Today, Corning's glass covers billions of devices. Smartphones, tablets, laptops, wearables, even some TVS and automotive displays. Different generations of Gorilla Glass are tweaked for different priorities. Some are formulated to be more scratch-resistant, others to be more drop-resistant, some optimized for folding devices. But the core idea remains the same. Start with a super clean, precisely formed sheet using fusion draw, then supercharge it with ion exchange to lock in a tough compressed surface layer. Think about how you treat your phone. It goes into pockets with coins and keys. It gets tossed on tables, dropped on the floor, maybe knocked off the bed at 2 a.m. If you did all that to a sheet of regular window glass that thin, it wouldn't last a week. The reason your screen usually survives is because of that invisible engineering, the chemistry that stuffs bigger ions into the surface, the precision that keeps the sheet free of flaws, the factories running non-stop to keep that quality consistent. Of course, Gorilla Glass isn't invincible. Drop your phone on the right corner from the wrong height onto a hard enough surface, and you can still get that heartbreaking spiderweb pattern. What actually happens in that moment is that the impact finally overcomes the compressive layer and drives a crack deep enough into the tensile interior, where the glass is stretched instead of squeezed. Once a crack penetrates that protective shell, it can race across the pane at incredible speed. That's why tiny chips or deep scratches can turn into big fractures later. They punch a hole through the armor, but consider the alternative. Without that armor, you'd be seeing those spider webs a lot more often. When Corning talks about the evolution of Gorilla Glass, a lot of it is about making that compressive layer deeper, stronger, and more damage tolerant, while also making the glass thinner and lighter. And if you do crack your screen, well, at least now you have a pretty good excuse to tell your friends exactly how impressive that piece of glass was before gravity finally won. If you want to see more episodes where we go inside the factories and processes behind the everyday tech you take for granted, make sure to subscribe, hit the bell so you don't miss the next deep dive, and share this video with that one friend who's always walking around with a shattered screen.